All right, let's look at the following problem. We have a hoop here that is rolling on the floor around the axis here. It's connected with a rod between that axis and the center of mass of the hoop. And all this will force the wheel or hoop to rotate along this dashed line on the floor. So the first question is, what is the omega of the hoop? Yeah, what I say here. And that means calculate the omega with respect to the center of mass, the point G. And that is here. And we are allowed to assume that the rod here at the distance r here is essentially massless. So then we know if we have a rotation, capital omega here, then we know for a circular orbit, the point here, the center of mass point, must be having the velocity according to the formula here. It's the well-known b equal omega times the radius. Only that now the omega is the capital omega. And a thing we know, if we're rolling this hoop at that distance, I mean that velocity, then here is the distance after a full revolution, the full time period, capital T. That's the distance that this point will be moving. And if there is no slippage against the floor, then the distance traveled is also the well-known formula, 2p times the radius. So then we get some information here. This formula here, time equal to pr over the velocity. And we know, right, angular velocity, that formula we know, 2p over t. And then we can insert this, we get this. And since the velocity is capital omega r, we get the final result here, that this angular velocity, that's the omega for the wheel rotating, spinning around the y-axis, that's that one. And it turns out it must be the same as the capital omega, which is over here. But wait a sec. It's not only this omega that the hoop is doing. Because if you think about it, after a while, the wheel or the hoop will be over here, for example. And then you realize that there must also be a rotation around the z-axis, right? So there is another omega around the z-axis. And we can realize that that omega is also the capital omega, but around the z-axis. So then we would like to find out the vector. So if you take the right-hand screw rule and think about the rotation about the z-axis here, then it will have the upward direction, the positive upward direction. And that is this part here, omega, and then EC here is just the basis vector, unit basis vector in the z direction. However, when that wheel is rotating in this direction, the right-hand screw rule will point that vector in that direction, in the opposite direction than y. So that's why you have a negative sign here. So the total angular velocity vector has two contributions. One due to that rotation around the y-axis, and one, the whole wheel here is also rotating around the z-axis, as we are going along this path here, the dashed path. So that's why we get this result here. And if you look at the length of the vector, then you just take this one square and plus this one square, and that's square root 2. So you will get the square root 2 capital omega as the length of this vector. Or if you like, simply the radial velocity as a scalar. Let's now turn to the next exercise, B. What is the angular momentum of the hoop? And when someone asking that question, it means the angular momentum with respect to the center of mass point, LG. So, and then the general rule is that the angular momentum is its relation to the matrix, moment of inertia matrix times the full omega vector. Unfortunately, we already computed the omega vector here. So all we need to find out is what is the matrix for that kind of thing with respect to the center of mass, and we have the coordinate system. The origin is in the center of mass. We have x here and y here and z here. The first thing we realize, since this vector here is 0 minus omega omega, that's what we have here, then we realize that whatever this element jxx is, it doesn't matter because it will be multiplied with 0. So we will not care even what gxx is. So we turn to the next one. This is jyy. And that is the momentum inertia with respect to the rotation around the y-axis. So it's rotating like this. And then for a particle, we know it's mr squared. And every element here is mr squared, and the sum of them will also be something like mr squared, and the total mass, so capital M here. So it will be mr squared for a hoop around the y-axis, and here is the z-axis. So if you rotate the hoop around the z-axis, in the problem text, we then got the information that should be the mr squared divided by 2. But it could also be shown like. So this is the matrix, and here is the omega vector here. So this times this times this, and this, that is 0. Then this times that, plus this times that, plus this times that. Yeah, that will be this one. And then this times that, and this times that will be this one. And written in this basis vector form, it can be expressed like this. So this is the final result for the angular momentum with respect to the center of mass point G. And the last question is, yeah, L equal J omega. That is something we learn even in kindergarten almost. But now it's a little bit more general form because it's a vector here and not just a number, and it's a matrix here. So what about, okay, are those vectors actually parallel or not? So we look at the omega. It's this guy here. So you see omega, right? C component 1, yeah. Minus for the y component, yes. And nothing in the x component. So this is omega written in a vector form. And in the same way, the angular momentum, I should have a g here also. Yeah, you can look here and you take out mr square omega, which is a scalar, boom, here. And what are you left with? 0, -1, and 1/2. And now you can compare those two vectors. And we can see there is no way that those can be parallel. Because you need something like similar here, 0, -1, 1, or 0, -2, 2, or something like that. And that we cannot get here. So they are not parallel in general. And for a little bit more complicated problem, it's not true. Okay, thank you very much. See you later.